Since we have missed 2 hours of lectures in the previous week, we'll have them back on Thursday, tomorrow. In the morning, understand you prefer 10:15 instead of 10, so we'll start at 10:15. We'll give you a lot of time to sleep. And since basically the last time we have seen the material, which we will continue now, is 2 weeks ago, I'll start with a few minutes of refreshing the stuff that we went through. So basically, we are dealing with angular momentum. Okay, we have written the operators Lx, y, Lz, and L square. We have seen that Lx or Ly or Lz commute with L square, so we can always build a basis where the eigenvectors belong both to L square and to one of these L's. Usually, traditionally, we say to Lz just because it's written in a more convenient way for in spherical coordinates. On the other hand, Li, Lj do not commute. The other epsilon I H bar, epsilon I J K. Okay, so we can choose one of them, we can't know all 3 of them, or even 2 of them. Okay. Then basically we defined an eigenvalue, an eigenvector equation. And we have defined 2 operators, L plus and L minus. And using their properties, we have shown that N must be smaller than L. We have pointed out that you have seen this already in modern physics when you have studied the properties of the hydrogen atom. Okay, so we're here. Now we would like to continue in the same spirit that we have employed in order to find out the eigenfunctions of a harmonic oscillator. We'll use similar concepts, similar tricks in order to find out what are the eigenfunctions of L square and Lz. Well, Lz we have already solved it, but and we will try to get more knowledge on M and L. Again, by what you know already from the hydrogen atom, you know that they are integers, but at the moment we haven't proved it. We only have proved that the absolute value of M must be smaller than or equal to M. Okay, how do we do it? Well, the same game. In the case of the harmonic oscillator, we took A or A dagger and tried to push the function below 0 in order to see what breaks down and what does it imply. We'll do the same game here. So instead of writing this whole YLM, we'll simply write it in the following way. And we will apply L minus on Lm and ask ourselves, what do we get? Okay. From where did we take that? Out of the commutation relation between L minus and Lz. I think we have given it in the previous lecture. Let me just check. Yep, it's appearing. Let's write it here. So I'll just write it down, transfer between the two sides, and we get what's written. Okay. What does that help me? Well, I can rewrite it in this case as L minus times Lz minus H bar. No problem. But this I know this operator I know to perform because I know what's Lz operating on Lm, on the eigenfunctions. It's just H bar n. This is just a constant. same eigenvector, sorry, the same vector. And we got here n minus 1 times h prime. What does it mean? Basically, it means that up to a constant, this is the eigenfunction, because employing Lz on it gives me n minus 1 times h bar, meaning that that's up to a normalization, some function, it's the eigen, the L and n minus 1 eigen. So because we have here two quantum numbers, L minus and n plus doesn't play with both of them, just reduces n by 1. Okay. So, cleaning up, the same game I can do for L plus, which will put here plus h bar n. Same game exactly, and I write already the normalization. Here. You don't see exactly from where the normalization comes. Go back to the previous lecture. We did it in the proof. Here, exactly the same. Okay, what does that tell me? It tells me that basically I know now how to progress. Why? Let's assume that n is equal a.
Can I ask you a question?
Sure.
This is L minus, right? The operator L minus and Lm.
Mm-hmm.
And then you said that it is equal to up to a constant to the same L minus over Lm.
And this is Ln minus
Then-
1 up to a constant.
Then why couldn't you like just right away conclude that? If you said that this is like, how did you conclude that it is equal to Lm minus 1 up to a constant?
Well, if I operate with L minus on Ln and see that Lz, the value for Lz is h bar n minus 1.
But where do you find Lz? Something doesn't.
Oh, you're completely right. The point is, okay, someone is here awake, and let me ask you, where do I see it?
I mean, like the commutation.
Oh, of course.
Yeah. Okay.
Yeah, otherwise, I couldn't use this commutation.
Yeah, that's why I got like, okay.
Fine, good. Happy someone is awake here.
Oh.
So the whole thing is I rewrite it as Lz times L minus minus Lz. Move from one side to the other, write it down, like that. Continue and get it.
So then you get that the Lz is what makes it go down by one like energy level?
Yeah. No, Lz gives you
Oh, the
operating Lz on the better write it this way. On this function gives you a constant times this function. What is it?
an eigenfunction of Lz.
An eigenfunction of Lz with an eigenvalue of h bar n minus 1.
Yeah.
Which means that the guy that appears here is just L on n minus 1.
Oh, because Lz gives you with the eigenvalue this state. Okay.
But
okay.
forces me to conclude that it's the eigenfunction with n minus 1. Because operating with an Lz on it gives me that result. Okay, if m is equal L,
Then you get
so if m, okay, let me do it this way. If m here is equal L,
0.
if m here is equal L, so I get here L times L plus 1, L times L plus 1, so it's 0. So what I said here, I can't go any further down. Sorry, here, in this case, that is the point. If I had here L at minus L, I would get here
No, just a minus.
just a minus, sorry. That's that. Also 0. I can't go any further down. And here, actually, without doing anything, I got to another very strong conclusion. It's hidden here in a small detail. If L is not a constant, is not an integer, what will happen? In one of these two edges, I'll go to a negative number, right? M must be integer, right?
Yeah.
Built in.
From like periodic.
No, because it was e
Yeah,
to
it's
the
not
power, it's 2 theta is periodic.
Yeah, so this
Sorry, phi is periodic. It goes on 2 pi. That's it. So m must be an integer. If m must be an integer, L must be an integer. Otherwise, in one of those limits, I'm continuing down or up because I get here a negative.
But then you can say only on the like bounds what happens in between. You can say for sure that it can't be like, non-integer in between.
Okay, we'll see how L behaves further on, but The only way you have to, but you can move here to the boundary, right? For any given L, you can move to the boundary.
Oh.
Right?
Okay, yeah, now I get it.
So, M integer we got it because the eigenfunction is 1 over 2 pi e to the I in theta, and it must be and it must be periodic in phi to phi plus 2 pi. So if m is integer, and looking on this, L is okay. Now, there is another operator that works similar to the behavior that we showed here for angular momentum, and that's spin. And spin, you know, is half integer. But if I let, this is like a parallel mathematical structure. I'm not going into what it is exactly, because as I told you, it's relativistic. We're not doing it here. But there, M is and therefore L, which has the same structure as here, is also half integer. So all numbers that are connected with either angular momentum and spin are either integer for angular momentum, or for spin could be half integer and integer also. It's bosons or Fermi. And that's all we have. Now, in parentheses, and without going into any detail about it, the only place that it breaks up is in two-dimensional systems. Rotations for two-dimensional systems, both spin and angular momentum can be other fractions. That's known as anion physics, and amazingly they are measuring it in quantum systems in the lab. That's quantum materials in two-dimensional systems. Can stop for a minute and ask, well, our universe is three-dimensional. Where can we build in the lab a two-dimensional system? And amazingly, a lot of stuff that you're using in your electronics here are on two-dimensional systems, just bounded between two differently doped semiconductors. The electron don't want to live in one or another, only on the surface of it, and these are two-dimensional systems. But in any particle experiment that we're known, that we're aware of, you have only half or integer spins. Even to the point of that quarks, where you have a third of charge, still their spin is half. Okay, so this is an extremely far-reaching conclusion that we got from a very simple mathematics. Okay, so basically this is the point where we can apply our either plus and minus, and find the eigenvector. Because we have now a differential equation. Apply L minus on the eigenfunction of L and minus L, or L and L, and it must be equal 0. That's relatively a simple differential equation. So to do it, we have to write L plus and L minus in full differential form. So I wrote the differential form of L plus and L minus. From where did I take it? A couple of lectures ago, I wrote Lx, Ly, Lz in theta and phi. And since L plus and L minus are just Lx plus minus I Ly, I can go back, copy the definitions of Lx and Ly and come up with this equation. One of the only places in physics that you run into a cotangents in an equation. Okay. And we know that trying to go one up from the LL state has to be 0. So I'm writing the equation. So what did I do here? I just wrote explicitly y, l, m, theta and phi, broke it up to theta and phi as we did again a couple of lectures ago. So a part that depends on phi, which is this guy, and a part that depends on theta, which is this large theta function. Just wrote it down, and all this is equal to 0. If all this is equal to 0, no point in copying what's written here. Okay? What did I do? Just perform the derivative, remind myself that it's not just general Lm, it's LL, and therefore it has to be L here. Perform the derivative on phi, which is easy. Just gets me IL down here. That's it. So I'll continue with it. So what did I do here? Nothing much. Moved this part here, divided by theta, and decided that I can't remember what is cotangles, and therefore I'm writing it as cosine divided by sine. Okay, this form we again ran into in the development of the eigenvectors of the harmonic oscillator. Not surprising, again, a differential equation of the first order. And what is the trick that we used here?
What do you mean?
This is complicated. How do I simplify it? We used this trick. Yes. Now life is a bit more complicated than for the harmonic oscillator because we have here this function. So let's write it down. If I perform integration on both parts, the integration of a derivative of ln theta is ln theta up to a constant. I just wrote an integration. don't seem happy. No, you're not happy on.
Something bothers me.
Okay. What bothers?
Why is it still ln eta?
Because integration on ln an integration over a derivative of a function is a function.
Ah, okay. Yeah, okay.
Nothing more, nothing less. The function could be as complicated as I want,
Yeah.
as long as it's continuous and has a derivative.
Yeah, okay.
So in this case, it's a logarithm.
Yeah, that's better. Yeah, yeah.
Wait. Can I ask you a question?
Sure.
Something doesn't add up. I mean, here you have like sine, and cosine is the derivative of sine, right?
But I haven't done anything yet. I've just.
No, but I'm saying if that's like the ln, and so you get ln at 0, which is minus infinity. So how would that happen?
Okay, let's see what happens here. Pay attention that you have a logarithm here on both sides.
Hmm.
But you're already seeing one step ahead. Let's get there and then worry about it. So difference is who cares? Okay. And now C prime I can just multiply inside. L, I write it in this way. And conclusion, which I'll write here. Some constant, and the constant I'll be able to find out of normalization.
Is there an n there?
Excuse me?
There's an n there. It's like ln of theta is. It's ln. No, it's not n.
For sine theta ln.
Ln. Okay. No, never mind. Okay.
Just because
Yeah, yeah.
one over sine is the derivative of the ln, and the internal sinus becomes cosine up to a plus minus. And this goes not up to it. Sinus goes to a cosine.
Yeah.
So actually, an integral of cotangents is simple.
I still don't feel like you have a point of singularity, like.
Yeah, but here I use I exponentiate both of them
Oh, you have minus infinity. Okay.
and get this, and minus infinity, e to the power minus infinity is 0, which is exactly what happens here with the 0, with theta equals 0. So everything's okay. Good, so we have the function YLL. חלוד אתה בשקט ובסוף. זה נבחן בסוף השיעור. Okay, so we have the YLL. Now we can produce everything in between. For any L, we can get YLL. We have it. Just a polynomial of sine functions, or sine function to the power of L. First, let's take care of the normalization. Just wrote down the normalization has to be equal 1. Jacobian. Somebody knows from where that comes?
No, not
Can you give you out principle? Can do it that way, can do it different ways. I'll let you see at home to come up, but it's just a finite integral. These are the results. And the only quirk I have here is the following. Because the only quirk is this, the minus 1 to the power of everything else is just from that. It's equal 1. First of all, I'm allowed to take the amplitude and put minus or e to the power of I whatever, still the same normalization. Why did I do it in this way? To connect it with the mathematics of spherical harmonics that I guess most of you have run into it at some stage, just because the way they define the normalizations of spherical harmonics. Okay, so after all this long story, we can write down YLL of theta and phi.
Wait, how did you take the 2 to the power L times L factorial outside of the square root?
As I said, check. Perform the interview.
Wolfram out.
Or Wolfram will perform it for you. Problem was basically giving everything, any mathematics you have to do to the computer to do, that you have to develop some taste when it's doing it wrong. Doesn't, well, I don't know if it doesn't happen much, but when it happens, you should have the feeling when it's wrong. I had I wanted to write down some programs that will draw a function, just a graph of a function, where I wanted that, which has x, y, z, I wanted to draw it in x, y, and ask for, and give the different values of z by the thickness of the line. So it's a way to show graphically a three-dimensional plot on 2 dimensions. Okay, so what do we do nowadays? We just try to write down a program in Python to do it. Okay, he's writing down, says supply your XYZ in this following format. Okay, very well, I take the code, I get my data in this format, nonsense. I go back to him and ask what's happening here. Oh, supply me the error message, supply. Okay, well, if you use this type of format to give the data, you should write the input differently. But sorry, you told me what is the form of putting in the data. So it's very helpful, but not perfect. So if you get something, always check. Okay, anyway. So we have YLL. Now we have Y, not N. 4 pi is because the 2 pi from this function. Everything else is just from the definition of the constant. Okay. Now, how will I get any Lm. Well, let's start from LL, which I know. And reduce it by L minus n times. Okay, then I have to take care of the normalization each step. And this procedure will give me following lovely solution. Long, ugly, and hopefully you'll never have to write it down as it appears. But that's a solution. Let's write down a few states just to get a feeling. Could someone guess the solution for 0, 0? It's easier than it sounds.
Constant?
Must be a constant. First of all, just let's take our one-dimensional type of intuition. If we have no potentials, place your any role in the theta field. It has to be the same everywhere. And because it's the lowest state, it can't have oscillations in it. So it must be a constant, and if it's a constant, it depends only on normalization. And since the solid angle is 4 pi, so it must be 1 over square root of 4 pi, and hopefully if you stick it into all the constants here, that's what you're supposed to get. If I didn't make a mistake here somewhere. Let's write down a couple more. Okay. You want to see drawings of it, you want to see higher spherical harmonics. There are endless number of sites on the internet that give you lovely pictures, whole descriptions for any M and L. Write you down the functions. The only thing I would like to emphasize here, basically, look on the difference between the term with M equal. For L equals 0, you don't have much choice. M must be 0 and that's that. For L equal 1, you have already three different possible quantum numbers for M, plus minus 1 and 1.
0.
Sorry, and 0. And we see it in the structure of the function, and basically you can see it here. Because what does an e to the power I phi tell us? It's like the eigenfunction of a one-dimensional free particle, right? Which has momentum. Here it's living on a circle, and therefore it has a function of phi. And plus minus is the one with LZ n equal 1 or minus 1. Then you can come to tell and ask me, why does it break symmetry? Why do I see here something on the Z direction and not on the X and not on the Y? The reason is simple. You decided to put your axis in the Z direction and calculate LZ. Therefore, you see it moving on a circle on the XY plane. That's it. Nothing more, nothing less.
How would I expect it to behave on X and Y too?
It will be, well, the easiest thing is to rotate your axis. The problem is that for the X and Y, if you insist on continuing on looking on the axis in the Z direction, it becomes ugly very quickly. And reasonably so. Okay, so now we can go on in two directions. One is to connect it with your knowledge with spherical harmonics, which I'll leave to tomorrow. First of all, you had today, I guess, enough heavy mathematics, and that's again not heavy, but a lot of details mathematics. And I would like to do here something that is new in the sense that we're going to deal with something that is more than necessarily a single particle, and that is adding up angular momentum and to see how you build up the structure. Why is it so important? It's important because most of particles that we'll run into in nature are composed. Let's say a neutron, a proton, it's 3 particles of spin half. Yet, when we're doing not too high energy experiments, we call it a neutron and a proton, and say it has L equals something and ML equals something. ML is, but it started from a system with L1, L2, L3 that could be in states M1, M2, M3. How do I combine that together? Even for a single particle, it's sometimes necessary. For example, an electron has contribution to its magnetic moment, both from the angular momentum. Think about simple high school physics, something moving in a loop has a magnetic momentum, but it has also a spin, which is another contribution. So yeah, if I'm asking what is the total angular momentum or magnetic moment exhibited by an electron, you have to take into account both the angular momentum and its spin. So how do I combine it? And the next reason is, I guess all of you have heard about entanglement, and you didn't hear a word about it in the course until now. And why is that? For the simple reason that I didn't have any systems that I could talk about entanglement, because there's no entanglement for a single particle in quantum mechanics, and until now we solved only single particles. So, I guess all of you heard this example of 2 particles, one with spin half down, one with spin half up, and they measured this one here and that one. How do I know that it combines actually to 0 and not to 1? And on all these, well, the answer is it could combine to 1. But how to combine them both, to say something on the angular momentum or the spin of the whole system, I need to know how to add spins or add angular momentum or add a combination of spin and angular momentum, and that we'll do after the break. So basically, I would want to start with an example. Let's say we have 2 spin half particles. Okay, so I have particle 1, which I know that the total spin is okay, because I know s squared, it's a spin half particle, and Sz could be only one of two possible states, plus minus each one of it. That is a result. Okay, as I said, we are dealing here with two spin half particles, and I just wrote what are the two quantum numbers for each particle that describes the particle. S squared, and in this case S1 square, and S1z, and the same for S2. So if I would want to write a wave function that describes both particles, I'll need 4 quantum numbers that tell me the whole story. The total spin would be S of the first particle S1 squared, total spin of the second particle S2 squared. In Z direction, I'll have either plus h bar or minus h bar for each one of these particles, meaning that de facto I have here how many states in total? Physics that you can count even without removing your shoes. For states coming from the fact that one particle has 2 states, the second particle has 2 states, and they're independent. So I have 2 times 2 states. So the answers to the questions that I asked in the beginning is 4. Those are all the states. Now, just to be less cumbersome, I won't write each time the two first numbers because they don't change. These are the properties of the particles. They don't give me any more information than what values n could take. So instead of writing this long description and even being simpler, an arrow up and an arrow down tells me h bar over 2 or minus h bar over 2 for each z component of one of those particles. You seemed worried?
So no, just making sure. So in order to like describe more particles, I just add more entries to my vector. Like here I have.
Yes, there are two problems in developing a many-body quantum mechanics. I'll describe them in a moment. And here we circumvent, actually, we circumvent one, and it's not yet a problem for the second one. Okay, one big problem in many particle physics is, let's look on this system. Looks benign, not very threatening, nothing to be afraid of. You'll add a third spin. It's clear what to do. A fourth one, an n1, n to the subsystem that exists on your table, like 10 to the 23 spins. No problem. I have a description, right? The problem is that your Hilbert space grows exponentially, 2 to the power n, where n is the number of particles. So if I'm taking such a Hilbert space and I want to describe a system with a Hamiltonian, which will have what is an Hamiltonian in the simplest form? A matrix, right? So its size would be 2 to the power L times 2 to the power L. 20, if you're very lucky. You have a very big computer, 24 perhaps. Spins is the most that you can feed your computer and diagonalize that matrix. So just your Hilbert space grows very quickly, and just brute force going and handling the Hamiltonian is hard. So either you find a way to simplify your system so you don't need all these states, or you're in a problem. Or build a quantum computer. You know, one of the big problems you hear all the time in the popular media. Okay, so you will build a quantum computer and will solve all our problems. The only problem is that the only real problem that quantum computers are really good in is simulating quantum systems. Because if you have a 24-bit system, you can simulate 24 spins, right?
Yeah.
Now you have systems of 100, so you can solve systems with 100 spins. 10 to the power 100, you can't write down a matrix in any classical computer that you can imagine. And even that's not true. That would have been true if our 100 bits won't decohere, won't lose their quantum properties on a reasonable time set. The states decay extremely fast, and that's why you need error corrections. You have to have a system that will compensate on the loss of data out of your quantum computer. So there is a solution.
But if that system is also quantum, then
No, actually there's a very elegant way around that I can't explain with you. But it's called quantum error correction, and that is putting one virtual qubit, or if you want spin, on many real quantum bits. And if you're larger than some size that depends on the number or on the rate of loss that you have in your system, you can keep this information forever. Although each spin by itself is leaky. But that is of the order of you need a few thousand bits for one virtual bit. So all quantum computing that exists at the moment can't keep one virtual bit for any reasonable time. So at the moment you don't have anything that really works. You have a direction, perhaps, if you would be able to scale to a few thousand bits and keep a quantum computer of a few tens virtual bits coherent, not decaying, then you have a start of something. So if you're optimistic, you say it's 5, 10, 15 years from now. If you're pessimistic, you say it's still way beyond what we can do. The other problem is you don't have good quantum algorithms. It's a second problem. Okay, but that's one problem. There's another problem that is even worse. And here I told you that I have spin 1 of particle 1 and the spin of particle 2. Okay, in classical physics, I can always say who is particle 1 and who is particle 2. In quantum physics, not always. What do I mean? Let's say, if the particles are identical, not identical, easy. You always can say who's 1 and who's 2. If you have an electron orbiting a proton, you know who's the electron and who's the proton, measure its mass. You're sure, you can't confuse it. If you have 2 electrons orbiting a nucleus, let's say helium, you never, in principle, would be able to say who is 1 and who is 2. Why? Because let's say you know that 1 is here and 2 is here. And then you let the system develop and measure again and see a particle here and particle here. Do you know that this particle came from here and this particle came from the second particle that you labeled at the time? No way, because you can't measure in between. So in many body, you have to somehow correct the labeling of particle 1 and particle 2. Why I'm not doing it here? Because I'm conceptually saying you know somehow who is particle 1 and who is particle 2. In all these entanglement measurements, one is going to Alice and one is going to Bob. So I know they're far away, they can't exchange. But if I'm looking on a local system, I never can say who is particle 1 and who is particle 2. It's meaningless. If you paid attention in statistical mechanics, you would know. Someone here studied statistical mechanics? Gibbs distribution. Gibbs was the first to ask what happens if I have n particles like Boltzmann and all the other guys, but I can't separate, I can't identify which one of them. So this situation and this situation is the same, you don't count it. So you have to build your Hilbert space. Let's say that this and this would be the same, because there's no difference between those.
And just don't take permutations, right?
So you have to build in permutations correctly, and the difference between bosons and fermions is how you build in permutations. So again, that's beyond what we do. We are doing the simplest many particles that we can handle. We are doing 2 or 3 particles, meaning that we never go beyond to the power of 3. 8 states, 8 we can again still count without removing our shoes. And we are assuming that I can say which particle is the first, second, third. Okay, so I have this structure. Now I say, I don't like it. I want to treat those two particles as one system that has some combined angular momentum. Okay, in classical physics, no problem. Go and build a state. Add the 2 vectors of the angular momentum S1 and S2. And you finished your problem. Start talking about the combined S, and here not to get confused, I'll replace it with J. Too many S's with too many. And that's that. Okay, but we never know S1 vector and S2 vector. We can't measure it. So, how do I build this description? Okay, let me guesstimate how this state looks, and then could show you how I do the calculation. Okay. How many states I will have under this description? I'll go back and ask one question. One step behind. If I'm moving from this description to this description, what did I actually do? We're already experts in quantum mechanics. We have a name to that. Change the basis. That's all I did. That's the only thing I can do in quantum mechanics. So the size of Hilbert space stays the same. I still have to have 4 states. So how do I have here 4 states? Let's look on the 2 limiting cases. One is that S1 and S2 are in the same direction, one they are in the opposite direction. Okay, if the 2 of them are in opposite directions, what will be the total spin? 0. So I should have some state that so J square will be equal to 0. That's the smallest value of J that I can get. The largest that I can get? 1. J square is equal, in this case, don't be confused, is 2H per square because it's L J times J plus 1. Okay, I'll write it explicitly. J times J plus 1. J is 1, so it's these are the 2. Can I get something larger? No, I can't get a total spin or that will be larger than J equal 1 and not smaller than J equal 0. For this state, what are the possible JMs, the M's in this description? No, half and minus half can't appear in a 0 state. We have learned if you have J squared or L square equals 0, what is the possible M of the component in the Z direction? If the total
zero,
it must be 0, it can't be anything else but 0. If for J square the J is equal 1, what are the possible JMs?
1 minus 1.
Yes, and?
0. Or maybe 0.
Yes, exactly. The mathematical structure is the same. You know already anything that you need to know about the structure.
Please redefine what JM is.
The Z component of the state J. We said the mathematics that describe it is the same for any angular momentum system.
Oh.
So if I decide to add up 2 angular momentums, I'm still in an angular momentum system. If I decide to combine angular momentum and a spin, it's That's more amazing, but I'm still in a mathematical structure that defines the combination of both of them. Okay. Now I pull up my hand and say 1, 2, 3, 4. I have all the states in the basis. So I can write this state as a 0, 0 state, and here I have a 1, 1 state, a 1, 0 state, and a 1, minus 1 state. That's my basis in this language. It's 4. Okay, I didn't change the size of the Hilbert space. Somebody here that knows a bit chemistry or spectroscopy? Singlet, triplet states. Singlet 1, triplet 3. Extremely important for lots of things in spectroscopy, chemistry, physics. Some of you heard about superconductivity, right? A pair of electrons. What is a pair of electrons? Such a thing. And this superconducting creature that is built out of two states could be in a singlet, meaning has no magnetic properties because J is equal 0 and it can't couple with a magnetic field, or a triplet. Two different classes of superconductors just coming out of this simple mathematics. Okay, so now I'm stuck in the following question. I have a basis. I have another basis. Both of them are good bases, no problems with them. I need to transform from one base to the other. Okay, let's see if we can make life a bit easier. Okay. Now, let me just copy what's written here to okay, I have to combine these two bases, write down a transformation, or what is a transformation here? Again, you're already experts in transforming from a basis to a basis. Just the most naive description of what do I do when I transform from a base to a base.
Oh, you do like a superposition of the base and then you find the...
I have to express this base function as some combination of these or vice versa. That's all I do in base transformation. They have to be unitarian and that gives me all kinds of rules, but that's, in the end of the day, all that I do. Okay, and two of the base two states, I can immediately identify the structure in base okay, this guy, it has two Z components, two contribution of Z components in the Z direction, right? Half and half. What will be Jm of this system? I measure each one individually. I see a contribution of half and half. What would be the total spin in the Z direction? One. Yeah, okay. I have only one such state here. Easy. This state and this state are the same. For the same reason. If I have two components in the Z direction that are H minus H bar over 2, the complete one has to be minus H, and this is the only basis state that has minus H as what you measure in the Z direction. Here, I have in the Z direction 0. Right, one up, one down. But I have here two states that contribute, that have a Jm state which is 0. And I'm not yet sure how to combine them. Perhaps one of them goes here and one of them there. Doesn't make a lot of sense because those are two symmetric, just changing why one of them will be J0 and the other one J1. Okay, so time for a bit of math to combine them. So, one good thing in life is that instead of a linear combination of 4 terms, I have now linear combinations of 2 terms. Hold it as right. Hard to argue about that statement. Okay. If it would have been classical vectors, I could exchange them and write 2s1.s2. They're not classical, I can't exchange. Okay, but when I'm breaking it up to Sx, Sy, Sz, and doing I can commute them because the X components commute the Y component. So, okay. So, what do these terms remind you of? They are angular momentums, but we had these combinations of Sx, Sy. What were they? Our good old friends S plus and S minus. Because they are built out of the X plus Ly and X minus Ly up to I's. So, I rewrite them as okay. Now I could write down brute force, but I want to guess a solution and prove it. Well, this is not yet guessing a solution. This is a solution. I just have to find A and B. But now I'll add a guess and decide that A and B are the same. If they are the same, plus normalization, they have to be 1 over square root of 2. And now, since I'm on a 2 by 2, what is the logic behind it? Well, there's no difference between this and this guy, right? Who cares if I call this particle 1, the second particle 2, and not vice versa? So the contribution has to be equal from both of them. If this is one of the contributions, the other guy must be orthogonal, the basis. So it has to be a minus. Now I go and change my base to be consistent. And this I replaced by okay, just replace the definition. And all these guys, all of them are eigen function of all these operators. Let's say, I just don't want to fill up the board with trivial but tedious algebra, but let's call this state 1. You know what, let's just write down one of the components. Let's say this whole structure in between them. Okay, so this guy is a total spin. It's half times 3/2, so it's 3/4 h squared. I took this guy. Okay. After operating, it's the same. It will remain the same. Okay. This guy is the same. This guy on this guy is up and down will be half and minus half, which is minus quarter, which is minus half. Okay.
H bar squared.
Squared, of course. Units are still conserved. This guy on this guy is, I'm pulling up this guy and lowering this guy. Doesn't, so this closes plus right up to, because this guy operates, this can't operate on this guy. So you have this, so you'll have to take it into account into the next matrix element. You go and do the calculation. You get for this guy 0, and for this guy what we wanted to prove. Right? One of them corresponds to 0, one of them corresponds to 1. So, till here, not the details. The details you have to take a quarter of an hour and sit down and write down all the matrix elements appearing here, but life could be shown, and that's the result. Okay, what have we learned from it? Two things. One, that there is a translation between one and the other, and the second is that without going and actually doing matrix elements between these combinations and finding A and B, I could always guess the result on very general physical ground. Now, in general, no matter how large it is, meaning S and S1 and S2 could have been 7 halves, who knows? And I want to write it down as J and Jn. All I need this way. Why? Because that's the general way that transform from a basis to a basis. And if you don't like that argument, sorry, can rewrite it. And what is this guy?
Matrix.
We have met it in the beginning of the course. That's 1. combination over all the basis of all the projection operators
Oh yeah.
over all the states is 1. So we just took this guy and multiplied it by 1. So I know exactly how to build this description. I wrote it up. Sorry about that. Okay, these are the amplitudes. If you want to impress your friends who are doing particle physics. Those are the Clebsch-Gordon amplitudes. You can find it in just Google Clebsch-Gordon components amplitudes or something like that. You'll find for any number of particles up to 3 or 4, for any values of J and S up to 5 halves, perhaps 7 halves, the whole table. And in the good old days, before there were smartphones or internet, any particle physicist who had some self-respect would go around in his shirt pocket with a small table that contains these components. And basically, I'm now debating with myself, you can go and I can show an example of calculating these components also for higher values. For these values, we have calculated them. Plus minus square root of 1 over square root 2. But for more complicated systems, it will be something different. I'm debating with myself if tomorrow to show you an example. How do you work? Again, there was a method of starting from LL, the highest values that we always know, and by operating with L plus and L minus, building up the whole structure. On the one hand, it's a neat trick. On the other hand, nowadays, everything is approachable, so it's very seldom that you need. I think that instead of understanding the general structure, understanding what stands behind this combination, understanding that in any case we can transform from one basis to the other is everything that we need at this point. And okay, so instead of that, I'll do entanglement, or the famous Bell inequality, the proof that quantum mechanics is the way to describe nature. There will start with 2 particles with total spin we know that are in a in a singlet state, meaning that we know that it's either particle 1 up and this particle 2 down, or the vice versa, and shows that I can convince you that the description of quantum mechanics is correct, and any other attempt to describe reality is wrong, or any other local way to try to describe reality is wrong. Okay, we'll talk on it in detail in the next lecture tomorrow at 10:50.
Thank you.
Thank you.
יש לי S1 Z כפול S2 Z והפוך, נכון?